Love all those answers up on the board. Let's take a look here. So how many protons does silver have? Again, this is related to our atomic number, which is the number at the top of our periodic square. So you are correct. Silver has 47 protons and must always, so silver must always have 47 protons because this 47 protons, our atomic number, is the identity of silver. If it had a different number of protons or a different atomic number, it would not be silver. Okay, so it has to always have 47 protons, has to always have an atomic number of 47. Now the number of valence electrons, though, taking a look at the outermost shell here, again, we can ignore everything in the center, just look at the outside. And at the outside, we can see it has one valence electron, so you are absolutely correct if you said one, which I see all of you did up here. So it only has one valence electron. Excellent. I do see some hands raised. If you have your notes open, feel free to start raising your hands right now. Again, you can get notes credit whenever, but if you also want attendance credit, you do need to do your notes during class and you do need to pass them. So make sure you do both those things during class. That way you also get attendance. Excellent, Landon. I see you in the chat. Let's go ahead and move on.
All right. So good morning, everyone. Just a couple of disclaimers as always. Please do not share any personal information during class. Your participation is vital and required. And all these class next sections are recorded for educational purposes. Let's take a look at where we're at this week. So we're starting off with a lesson called Periodic Table Families. We are on day 19 of 60 in week 5 of 13, so approaching just halfway through the semester. Our unit today, we just have 2 more lessons after today's lesson, so we're approaching the end of Unit 2, quickly approaching the due date for the Unit 2 project, which is April 15th, or this Friday, or excuse me, Thursday. All right, so just keep that in mind. Today we'll be able to explain how the periodic table is organized by groups based off of their valence electrons. And we will also learn how to describe the properties of several groups, including alkali metals, halogens, and noble gases. All right, all that will start to make more sense as we get more through the today's lesson. All right, let's start raising our hands for the notes.
All right, looking good. I do see Landon and Julie in the chat box. Let's get some more people raising their hands to open up the notes. Again, those notes links are in the chat. You can also go to the grades tab. Everything's always in the grades tab as well. You have 20 more seconds to raise your hands. Just taking a look here. I'm waiting on Callie, Thalia, Ryan, Angelo, Anthony, Elijah, Marina, Douglas, and John. Go ahead and raise those hands or send me a chat once you have your notes open and ready to go.
Let's start off with a little bit of a brainstorm this morning. Looking at all these elements, right? We all have the Bohr models of all the same group of elements in the periodic table. They are all in group 16. So what is the same in each Bohr model of these group 16 elements? What do we notice, or what should be all the same? Yes, very good. They all have 6 valence electrons. So if we count, oxygen has 1, 2, 3, 4, 5, and 6. If you'd like to, going all the way down to this very large element, plutonium, we have 1, 2, 3, 4, 5, and 6, always in group 16. Remember, looking at the last digit. So what is the thing that's different about all these elements, though? Just looking at these Bohr models. A little more obvious. Again, looking at the electrons, what is different about each element here? What can we see? Yeah, they all have different shells, but I was looking for a different amount of shells. But yeah, you guys are getting there. So again, if they are all in the same group, each element should have the same amount of valence electrons, which we did confirm. But each group will have larger and larger amounts of shells as we go down that group of elements. So oxygen being at the top, it has only 2 shells. Plutonium all the way at the bottom has many, many shells of electrons. Let's move on to our first topic here, looking at periods. So periods in a periodic table are just the rows, are what we call rows in the table itself. So elements that are all in the same period should all have the same number of shells. All right, so if we read across the table left to right, horizontally, that is a period, and they all have the same amount of shells, which is what we just looked at. The small shell can only fit 2 electrons, but bigger shells fit 8 electrons, right? So for number 2 in your notes, go ahead and mark row and raise your hand when you're ready to move on. I'll give us a timer. All right, so now instead of the row or period, now let's look at the column or group. So every element in the same column or group will have the same amount of valence electrons as we've seen before, right? But as we go down that group, right, as we go from top to bottom, as we get lower, the element is going to get larger in terms of how many shells it has. All right. The other thing to keep in mind about groups is that all elements in the same group have the similar properties, and we will look at we'll discuss that a little later on. So for number 3, go ahead and mark column in your notes for number 3.
All right, looking good. So let's go ahead and just take a look at a visual of this. Again, we've kind of seen all the descriptions, but let's make sure we understand how to visualize it as well. So again, taking a look at this main idea over here, each group or column up and down are families, sometimes called families. They have the same number of valence electrons. So group 1 has 1 valence electron. All of these atoms have 1 valence electron. Group 2, they all have 2 valence electrons up and down. Group 13, remember, take a look at that last number of 13, has 3 valence electrons up and down. Group 14 has 4, all the way down to group 18, which has 8 valence electrons. Go ahead and give me a green check, orange X, if that visual helps me solidify it a little bit more in your brain. Again, all of the ups and downs have the same number of valence electrons. The number of the group is related to the number of valence electrons. That last digit is identical. Excellent. All right, now on the other hand, taking a look at our rows, again, periods are rows left to right. They all have the same number of shells, so as you get down to higher and higher periods, you have more and more shells. So taking a look here, period 1. Period 1, they all have 1 valence shell, that small valence shell that only fits a total of 2 valence electrons. Period 2, they all have 2 valence electrons, they're a little bit bigger. Period 3, even bigger, they all have 3 valence electrons. So as we go down the periodic table, they're getting bigger and bigger. The periodic table is highly organized, and this organization is to our benefit. Okay, let's go ahead and talk a little bit about reactivity.
Reactivity is something that it's a property that we deem to a specific element that describes how it reacts with other conditions or other elements. So some elements rarely react with each other because they have a full valence shell or equaling 8 electrons, or I'm sorry, 8 valence electrons. So this is something that is specifically part of the noble gas group, as we can see on the right-hand side. They are called the noble gases because they do not need to gain or lose or share electrons with any other element or chemical, i.e. they do not bond with anything. So keep this name in mind. They are very noble in the sense that, right, if you have nobility, like in feudal society, they don't like to, they kind of look down on all of the peasants or the clergy, and they like to be by themselves, all right? And then one exception with the 8 electron rule, keep in mind that helium right here has 2 electrons, but still it has a full, very small shell of 2 electrons. It is still a noble gas.
All right, so on the other side of the periodic table, we have the most reactive elements, literally on the left side of the periodic table. So these are elements that are very, very reactive, and the reason is because they're close to being stable. So this is important to understand. If you are stable, you are not reactive. If you are stable, you are non-reactive. You don't want to bond. If you are close to being stable, you are highly reactive because you're so close to being happy that they are going to be very aggressive in filling their shell or losing their shell. So there are actually 2 groups that are the most reactive on the periodic table, and it doesn't necessarily have to do with whether or not they gain or lose electrons. It has to do with how many they gain or lose. So for example, the alkali metals, group 1, which contains lithium, sodium, potassium, etc., they all only have 1 valence electron because they're in group 1. And so in this case, would they rather gain 7 valence electrons or lose 1? Tell me in the chat box what's easier. Would they rather gain 7 electrons or lose 1? Yeah, it's going to be way easier to just lose 1, right? And that's really going to make them extremely reactive, extremely aggressive, because they only have to lose 1, right? To drop down to a shell that's already full, they just have to lose this single one. So they're going to be highly, highly reactive because, again, they're only dealing with 1 electron. Okay. On the other hand, it could also be if you're just gaining 1 electron. So taking a look here, fluorine, chlorine, and bromine are all in the halogen group, or group 17. Taking a look at the ending digit of 17, the group number, that means they all have 7 valence electrons, which you can see over here. Fluorine and chlorine both have 7 valence electrons. So in this case, are they going to want to lose 7 or gain 1 to get to their total of 8, their total octet? Are they going to prefer to lose 7 or gain 1? Yeah, they're going to prefer to just gain 1, right? So they just want to gain 1. Much easier to gain a single one than to have to try to lose 1. Okay, sorry. Okay, so in this case, again, they're only dealing with 1 electron, though. So again, it doesn't necessarily matter if they're losing or gaining electrons. It just matters how many. So they are both super close. One just has to lose 1, one just has to gain 1 to get to a full shell, and therefore they are extremely, extremely reactive. Taking a look at the summary here, again, group 1 you can see is labeled as very reactive, and group 17 is also labeled as very reactive. The two most reactive groups on the periodic table, because this group only needs to lose 1, this group only needs to gain 1, and so anytime you're only dealing with 1 electron, that makes you extremely reactive regardless of if you're gaining or losing. One more time, green checks, orange checks, if that makes sense. Again, doesn't matter if you're gaining or losing. If it's 1 electron, you're highly reactive. Great. Now taking a look then at the alkaline earth metals, right? They have 2 valence electrons, so they actually need to lose 2. So they're still reactive, but not nearly as reactive, right? Because they have to lose 2, which is going to be a little bit harder than just losing 1, right? They have to lose 2. And again, noble gases are not reactive at all because they're already stable. Again, if you are stable, you're not reactive. If you're close to stable, you're very reactive. So in this case, they have all 8 of their valence electrons, or helium has all 2, and so they are already stable, which makes them inert. Inert is just another word for non-reactive. All right, so go ahead and on the whiteboard, let's apply this. Which of the following atoms would probably be the most reactive? Again, think about which group here either needs to only lose or gain 1 electron. Go ahead and circle the answers up on the board. Again, it doesn't matter if you lose or gain as long as it's just 1 electron. Go ahead and circle the correct answer. Awesome. All right, I'm seeing lots of good answers up here. We said an alkali metal with 1 valence electron. Again, it has 1 valence electron, so is it going to rather lose 1 or gain 7 more to get to a full octet, a full 8? Tell me in the chat, this alkali metal, all of these group 1s right here, would they rather lose 1 or gain 7 more? Lose 1 or gain 7 more? Yeah, they're actually going to prefer to lose 1, right? That's going to be a lot easier than trying to gain 7 more. Alkaline earth metals, on the other hand, need to lose how many? Alkaline earth metals, they need to lose how many? They have 2 valence electrons, so to drop down to a full shell, they need to lose how many? Tell me in the chat. Yeah, they need to lose 2. And then same thing if you're in the boron family with 3 valence electrons. Is it easier to lose 3 or gain 5 more to get to a total of 8? Is it going to be easier to lose 3 or gain 5 more? Yeah, in this case, lose 3. So again, it doesn't necessarily matter whether or not they're losing or gaining. It just matters numbers. So right here, the 1 tells us that this has the least amount to lose to become stable. It's the closest to being stable, making it highly reactive. This is number 4. Please raise your hands for number 4 when you have that completed in your notes. You have 20 more seconds to get that done. I do see a lot of you already have it. Go, go, go. Raise your hands or send me a chat. All right, so this one you need to complete on your own, so please don't put answers in the chat. So this time we want to know which of the following atoms would be most reactive. Again, it doesn't matter if they're losing or gaining. In this case, they're all going to gain electrons, but you need to think about which one's going to gain the least amount of electrons, again, to get to a total of 8. Right, so in this case, these ones all need to gain. So to get to a total of 8, right, our octet, think about which of these needs to gain the least. A pnictogen with 5 valence electrons, a chalcogen with 6, or a halogen with 7. Think about which one needs to gain the least to get to a total of 8. This is number 5. You have 30 seconds to get this done. If you need help, we're in the Q&A chat. So please communicate with us. Go, go, go.
So first we have the alkali metals. The alkali metals are characteristically known as being highly reactive, especially with water. They all have one valence electron that is easy to lose, which explains why they are all have that high reactivity in terms of metals. Group 2 are the alkaline earth metals, and they are reactive but less than alkali metals. They have one more valence electron for a total of 2 that they want to lose to have a full octet, and they include elements like beryllium, magnesium, and calcium.
All right, so groups 3 through 12 are kind of the weird elements of the periodic table. These are what are called the transition metals. You can see them down here. They're kind of the shorter columns, the ones that are tinier. And the reason that they're the weird groups is because they can create a lot of compounds even if you have the same exact atoms involved. So for example, iron can bond with oxygen in multiple ways. Even though they're the exact same atoms, they're going to bond in different ways, which is not true with a lot of our other elements. So specifically, with transition metals, they don't follow all the rules that we've been learning about, which is fine. They follow different rules that you might learn if you ever take a course in chemistry in college or later on in life. But for our purposes, they're not following the rules that we've been talking about. Not a big deal though. We can still learn some important things about them. So group 8, which is right here. Okay, in group 8, their outer shell is actually not full. So this is kind of crazy to think about. They do have 8 valence electrons, and we've been talking about that octet rule, but the iron family does not follow the octet rule. So they do have 8 valence electrons, but technically they actually need more to have their outer shell be full. All right, so that actually means that they're technically not full. However, with that 8 electrons, 8 is still a good number, and so they do end up being very strong with high melting and boiling points. Go ahead and give me a green check or an orange X if that makes sense. Green check, orange X if that makes sense. Again, it's technically not full, which breaks the rule we've been talking about. But it does still have 8, which is still a strong number, even if it's technically not full. Excellent. Karema, let me know if that makes sense. Gustavo, Mary, Ryan, Elijah, let me know if that makes sense, everyone. Thank you, thank you. Looking good. Awesome. Now the other one of the groups I want to talk about in the transition metals is group 11, which you can see right here. All right, so group 11 is also called the copper or the coinage family. Reason being because they've all been used to make coins throughout history. You can see some examples down here. So copper, silver, and gold have all been used to make coins. That's also called minting coins. But not only that, they are also strong conductors of electricity. Now, we don't use silver and gold very often in our electronics because they're very expensive, and if we do use them, we use them in small amounts. But we use copper all over the place. All of the wires in your house are probably made from copper because copper is cheap and it's also an excellent conductor of electricity. Go ahead, give me a smiley or an emoji in the chat if that makes sense. Again, this is another kind of weird element. It acts strange, right? Not according to the rules we've been talking about, but it's still a really important family. Excellent. All right, good. Let's go ahead and match these up for me on the whiteboard. All right, group 1, alkali metals, group 2, alkaline earth metals, group 8, the iron family, group 11, the copper family. For the simple ones, right, group 1 and group 2, remember that group number is related to valence electrons. So if you need a hint on those ones, because I know they look similar, again, the group number is related to the number of valence electrons. Go, 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 get your answers up there. Yeah, so let's look at the cleaned up version here. Group 1 has 1 valence electron. Again, we talked about how they're highly reactive because they only need to lose 1. Group 2 has 2 valence electrons, making them still reactive, but not as reactive, right? Because they have to lose 2, which is a little bit more. Iron family is a transition metal. Again, their shell technically isn't full according to our rule. They break that rule, but they still do have 8 valence electrons, making them still strong. So they have high melting and boiling points from that strength. And copper family, another transition metal, a weird metal. These ones are strong conductors of electricity, like copper is used throughout our houses, and they've all been used for coining, for making coins. All right, you have 30 seconds to go ahead and fill out number 6 and raise your hand.
Now on the verge of the metalloids, and first row of the nonmetals. So let's take a look here. Group 13 or 3A is known as the boron family because the leading element on the top of that column is boron, which is kind of like the top edge of that metalloid barrier that we saw in previous lessons. All elements in this group have 3 valence electrons that they want to lose. So thinking about stuff like aluminum, gallium, indium, they all have very similar properties. So if you just think about aluminum, like aluminum foil that you use to cook with or wrap food in, it's very malleable and ductile, and but it's also very lightweight. Group 14 or 4A, known as the carbon family, these are all mostly nonmetals with a couple of metalloids being silicon and germanium. Carbon is important because it's literally the building block for all living or organic compounds on Earth. So if carbon didn't work the way it does, we wouldn't be here alive or having class. Um, the reason it's able to do this is because it has 4 valence electrons. So if you have 4, which is half of 8, right, you'll be able to bond by giving 4 valence electrons away or accepting 4 more valence electrons, and, equally in any situation. So carbon being very versatile, and silicon also being very versatile for making that technology that we use almost every day. So very important group of elements. Go ahead and give me a smiley emoji or a smiley face or a yes in the chat if this is starting to make sense.
All right, so let's take a look at pnictogens and chalcogens. Pnictogens are group 15. Again, looking at the ending number, that means that they have 5 valence electrons. Group number is always related to the valence electrons, and so they just need to gain 3 more. Pnictogens are actually the most diverse group on the periodic table. They contain nonmetals, metals, and metalloids. So 2 nonmetals, 2 metalloids, and 1 metal. An example of which is nitrogen. Remember, we do have a lot of nitrogen in our atmosphere. We actually have more nitrogen than oxygen in our atmosphere, but because of that oxygen, we can still breathe. Pnictogen, though, means to choke, because if we had an environment entirely of nitrogen, we would choke. All right, so that's where that word comes from, the Greek pnictogens. All right, chalcogens, group 16. These ones tend to form strong compounds with strong unpleasant odors, the most significant of which is sulfur. All right, so if you think about the rotten egg smell, that is what's called hydrogen sulfide. When sulfur bonds with 2 hydrogens, that is the smell of rotten eggs, and in high amounts, it can actually be poisonous and corrosive. Not to mention, it stinks real bad. All right, now again, group 16. Take a look at that ending number. Group 16 has 6 valence electrons, just needs to gain 2 more. So chalcogens are pretty reactive, not as reactive though as our halogens, which we've mentioned multiple times. This is group 17, ending number is a 7, so they have 7 valence electrons. They only need 1 more. Again, anytime we're dealing with 1 electron, either gaining or losing, that's the most reactive groups. And interestingly enough, they're the most reactive with each other. So group 17, which only needs to gain 1 electron, and group 1, which wants to lose 1 electron, they actually work together. So group 1 will give its electron to group 17, and they bond extremely readily. They are highly reactive with each other, and they form what are called salts, the most common of which you know in the that's at home is sodium chloride, NaCl. The Na, the sodium, is an alkali metal, and the chlorine is a halogen. Go ahead and give me a smiley or an emoji in the chat box if that makes sense. Again, the word halogen actually means salt formers. That's where that comes from, the ancient Greek for salt formers. Excellent. So that includes fluorine, chlorine, and bromine. And again, group 18, we are really familiar with. That's our noble gases. Group 18 is, they have all 8 of their valence electrons, right? They end with the number 8. And that actually makes them stable, right? Because they have full octets. Full octets. Again, the exception being helium. Helium still has a full shell, but again, that small shell only fits 2. So it's still full and still inert, still stable, still non-reactive, but it only fits 2 electrons. Okay, and that it contains helium, neon, argon, krypton, all of the ones that we can use in neon lights to create plasma, our 4th state of matter that we talked about in Unit 1, to create these really cool colors that you see up on the board here. All right, go ahead and take a look at question number 7. This one you need to go ahead and complete on your own. If you need help, we're in the Q&A chat. Okay, so we need to look at pnictogens, chalcogens, halogens, and noble gases. How many valence electrons are there, and what are some characteristics? So 6 valence electrons, the salt formers, 7 valence electrons, 5 valence electrons, or the non-reactive elements. All right, remember, if you do need help, the group number is related to the number of valence electrons. So again, look at those ending numbers if you need help. All right, this is going to be number 7. You have 30 seconds. Go, go, go. Raise your hands.
Periodic table and what they all have similar and what's different about them. We learned about the different properties of the different groups of elements, such as halogens, noble gases, alkali metals, and so on. All right, I can see that we all are doing pretty well with the quiz. So if you haven't already, please go ahead and submit your quiz. If you do not have anything else or have no questions, please feel free to let yourselves out and have a great day.